everyone. We're going to continue with chapter 5, and now we're at section 5.5, the exponential random variable. What is an exponential random variable? If you have a random variable x that has a density which is lambda e to the minus lambda x when x is positive and 0 otherwise, with lambda bigger than 0, you do need lambdas bigger than 0, otherwise this function right here f will be negative, and you need that a probability density function is always non-negative. So if x has this kind of density, then it is said to be an exponential random variable with parameter lambda. Okay? In practice, where do you see exponential random variables? Exponential random variables are random variables that measure things like the time for the next rare occurrence. So the time starting now until the next rare occurrence. So for example, the time from now until the next accident on the intersection of Alafaya and University, or the time from now until you get the next wrong number phone call, or things like that. That's an exponential random variable. Okay. So this is the probability density function. What about the CDF of an exponential random variable? The CDF of an exponential random variable, f of x, will be the probability x is less than or equal to little x. Well, since you know that the random variable is never negative, which you know because the density is 0 when x is less than or equal to 0, you know that this is 0 if x is less than or equal to 0. How about if x is bigger than or equal to 0? Well, this will be the integral from 0 to x of the probability density function of the exponential random variable. Okay, so that's the integral 0 to x lambda e to the minus lambda t dt. And plugging this in, just do a little integration by u substitution. U equals negative lambda t, so negative lambda dt will be the derivative. So you have minus e to the minus lambda t going from 0 to x. Plug in x, plug in 0, it's minus of that, so you get 1 minus e to the minus lambda x. And that is your cumulative distribution function for an exponential random variable. Okay, and of course you can check when you differentiate this with respect to x, you do indeed get the PDF that we've written above. Okay, so I just should write again over here that this is when x is bigger than 0 and 0 when x is less than or equal to 0. Okay, so that's just being complete, writing down what the entire cumulative distribution function is. Okay, so for this exponential random variable, let's next try and find out what the expectation and the variance are. Okay, so let's take a look. Expectation of the random variable and the variance of the random variable. Okay, so the way we're going to calculate the expectation and variance is actually quite a nice technique. What we're going to do is we're going to find out what the expectation of x to the n is. Okay, so assume that n is positive. Okay, and we will try and find out what expectation of x to the n is. Okay, so what is this? By the formula of expectation of a function of a random variable, we know that this will be integral from minus infinity to infinity, x to the n times the probability density function. Okay, so we know that'll be the integral from 0 to infinity, x to the n times lambda e to the minus lambda x dx, because the density is 0 to the left of 0. So you are going to start at 0, and this is the density. All right, what we're going to do now is do a little bit of integration by parts. We will let u equals x to the n Then du is nx to the n minus 1. Okay. And we let v prime be lambda e to the minus lambda x. Then v will be minus e to the minus lambda x. Okay. So what will this integral be? It'll be u times v going from 0 to infinity minus integral u prime times v. So v is minus of that, so I'll just put a plus there. Okay, and let me just box this off. Okay, so let's see. I mean, really, yeah, technically we're supposed to do limits over here. Take a limit as b goes to infinity, and plug in b for x and plug in 0 for x, and this will be just 0 minus 0, so that's gone. That's just going to be 0. How about this? This will be n times the integral 0 to infinity x to the n minus 1 e to the minus lambda x dx. Okay, and what do you have over here? Well, let's look at this part over here. Let's put a lambda in there, and let's put a 1 over lambda over here. Okay, lambda is non-zero, so you can do that. We have lambdas bigger than 0. Okay, and so now stare at this for a moment and take a look. What do you see that to be? Compare it with this if you need, and you see that that was expectation of x to the n, and this is expectation of x to the n minus 1. So you have this identity. Expectation of x to the n is n over lambda expectation of x to the n minus 1. Okay, now let n equals 1, and what do we get? We get expectation of x is 1 over lambda expectation of x raised to 0. But what's x raised to 0? That's 1. What's the expectation of 1? That's just 1. So this is just 1 over lambda. So very nice. Now we have the expectation of x. Okay, beautiful. And now let's find the variance of x. So we will need the expectation of x squared. What will that be? So you will let n equals 2, and what do we get? Expectation of x squared will be 2 over lambda expectation of x to the n minus 1. That's 2 minus 1, which is 1. Okay, so that is 2 over lambda, and what is the expectation of x? We just found out that's 1 over lambda. So that's 2 over lambda squared. That's the expectation of x squared. And so the variance of x, we know, will be expectation of x squared minus the expectation of x whole squared. And so that's 2 over lambda squared minus 1 over lambda squared, and that will just be 1 over lambda squared. Okay, so that's quite nice. We have these results. Expectation of x is 1 over lambda, and variance of x is 1 over lambda squared. Okay, for exponential random variable. All right, and what we'll do now is let's take a look at some examples, and then we'll come across a pretty nice property of an exponential random variable. Okay? Okay, so okay, so suppose that the length of time that it takes for somebody to be served at a ticket counter is lambda equals 1 over 5. Okay, so the length of the time that it takes for somebody to serve at a ticket counter is an exponential random variable with lambda equals 1 over 5. So service time at a ticket counter is an exponential random variable okay, or actually let me just write the time to be served at the time that you're served at a ticket counter is an exponential random variable with lambda equals 1 over 5. Okay, so let's find the probability that you are served oops for more than okay, and part 2, find the probability that you are served five and 10 minutes. Okay, all right, so we have that the time that you were served, that's an exponential random variable. So let's suppose x is the time that you are served. And we know that the density of x is lambda e to the minus lambda x. Okay, so we know that that's the density of the random variable. Okay, all right, so what do we want? Part 1, we want what's the probability that x is bigger than 5? Okay, so what will that be? That'll be the integral from 5 to infinity of the density, right? We don't have to do anything with the interval because throughout the interval from 5 to infinity, the random variable is got the density is non-zero. Okay, so that's integral from 5 to infinity of 1 over 5 e to the minus 1 over 5x dx. Okay, use substitution, and you know this is minus e to the, or let's just write x over 5 going from 5 to infinity. Once again, yes, I should write b and take a limit as b goes to infinity. And so when you have the top limit and take a limit as b goes to infinity, you get 0. And then for the bottom limit, you plug in 5 and you get, you get minus of minus e to the minus 5 over 5. So what do you get? You get e to the negative 1, okay, which is approximately 0.368. Alternately, you could have over here just said the probability x bigger than 5 is 1 minus the probability x less than or equal to 5. So it's 1 minus f of 5. And so it is 1 minus, and if you recall, what is the CDF of exponential random variable is 1 minus e to the minus lambda x. So it will be 1 minus e to the minus 1 over 5x. Over here x is 5. Okay, and so that's e to the negative 1. The 1 minus 1 cancels, and that's what you have. Okay. So pretty straightforward there. Second part, you're asked what is the probability that x is between 5 and 10? Well, this is the same as the probability that x is less than 10 minus the probability that x is less than 5, right? You can split it up like that. So this way directly we can use the CDF, and that is f of 10 minus f of 5. Okay, so that is 1 minus e to the minus 1/5 times 10 minus 1 minus e to the minus 1/5 times 5. All right, so that's minus e to the negative 2 minus of minus e to the negative 1. So that's 1 over e minus 1 over e squared, if you like, or e minus 1 over e squared, and that is approximately 0.233. Okay, so once you have it set up, the calculations are pretty straightforward. Okay, so now let's discuss this neat property of exponential random variable. So what you have with an exponential random variable is that the random variable is memoryless. Okay, so to look at what this is, first let's look at the definition of memoryless. A random variable A random variable is said to be memoryless if the probability that the random variable is bigger than s plus t, given that the random variable is bigger than t, it's the same as if you started at time 0 and you wanted the random variable to be bigger than s. So this is just the same as the probability that x is bigger than s. Okay, and of course you want that s's and t's are all positive or non-negative. Okay, so this is what you mean by a random variable being memoryless. Okay, and we have that an exponential random variable is indeed memoryless, but you can verify that by plugging in the probability density function or doing the integration, etc. You can see that this works out. Anyway, let's just look at one further property. So we'll use the conditional probability formula, and you have probability of A given B is the probability of A intersect B divided by the probability of B, and it is memoryless. So this is equivalent if that left hand side is the probability of x bigger than s. Okay, well, let's study this. What is the probability that x is bigger than s plus t intersect that x is bigger than t? You want the intersection of these. Well, obviously over here s plus t is bigger than or equal to t because s and t are both non-negative. So the numerator is the same as probability of s bigger than s plus t. Denominator stays, and that is probability x bigger than s. And you cross multiply and you have this neat little property for a memoryless random variable is probability x is bigger than s plus t is the product of the probability x is bigger than s and the probability x is bigger than t. Okay, that's quite nice. This over here you have is a definition. Okay, so that's a definition, and this is an equivalent statement that you could write for a memoryless random variable. And you can check for an exponential random variable, you can plug it in and check that what is the probability x is bigger than s plus t. So let's say x is exponential with parameter lambda, the probability that x is bigger than s plus t, well, it is 1 minus f of s plus t. So that's 1 minus e to the minus lambda s plus t. Okay, so that's just e to the negative lambda s plus t, which is e to the minus lambda s times e to the minus lambda t. And this, in the same way, you can see that this is 1 minus f of s, and this over here is 1 minus f of t, the CDF, where capital F is the CDF. And so that is a probability that x is bigger than s, and this is the probability that x is bigger than t. So clearly, if you have an exponential random variable, you have that it's memoryless. Okay? And I want you to read the examples in the book. One example in the book 5C that's quite a cute one. It talks about people being served at a post office. It's pretty straightforward. Take a look at example 5C from the book. And let's do one more example. And here it is, okay? We'll look at example 5D. All right, and here we're going to look at it in both a general situation and also an exponential situation. Okay, so suppose that the number of miles that a car can run before its battery wears out is exponentially distributed with an average value of 10,000 miles. Okay, so the number of miles that a battery can run is exponential with an average of 10,000. All right, so number of miles Okay, so let's be careful over here. You suppose you have x is the number of miles that the battery runs. What kind of random variable is this? X is an exponential random variable. And what is lambda? You remember, if you have a random variable that's exponential x, then its expectation is 1 over lambda. So this is average of 10,000, so that is its expectation. So that is 1 over lambda. So lambda is in fact 10,000, and you could just write lambda equals 10, and the units are in thousands of miles. All right, in the book they've done this, so I'm just going to stick with that there. Writing lambda equals, I should write 1 over 10, where units are in, for the miles are in thousands of miles. Okay, so x is exponential with lambda equals 1 over 10. All right, the question says, if a person desires to take a 5,000-mile trip, what is the probability that he or she will be able to complete the trip without having to replace the car battery? What can be said when the distribution's not exponential? Okay, so first situation, they're saying, okay, assume like we have it that the battery life is exponential. Second part, they're saying, what if you do not have an exponential distribution? All right. So what do we want? We want to take a 5,000-mile trip. Okay. And we're starting right now. Because it's an exponential random variable, it's memoryless. It doesn't matter how many miles a battery has already run. All we're asking is the lifetime starting now of the battery. What's the probability that that lifetime is bigger than 5? Right? And this is because of the memoryless property of the exponential random variable. Okay, so what is this? This is just 1 minus the cumulative distribution function of f evaluated at 5. And that is 1 minus e to the minus lambda times 5. Okay, so that's e to the negative 1/2, which is approximately 0.607. Okay. And now let's see what would be if lifetime was not exponential. Okay, if it's not exponential, then it does depend on how long you've run the battery so far, right? So then you're asking yourself, well, the battery's running right now. Okay, so you know, let's say now, right now, the time since the battery was since the battery first started, or since the battery was new, let's say right now the time is t. You're asking what's the probability that given that it's run till now, that given that the lifetime is at least t, what's the probability it runs an additional 5,000 miles? So what you're asking is the probability that the lifetime is bigger than t plus 5, given that the lifetime is bigger than t. That's really what you're asking. If even if it's exponential, if you write it down like this, things will cancel and give you what we had above. Okay. But in particular, if it's not exponential, then you do have to go through this whole thing. All right. So then just using the conditional probability formula, you have x bigger than t plus 5 intersect x bigger than t over the probability x bigger than t. Okay, the numerator intersection simply the probability x bigger than t plus 5. Denominator is the probability x bigger than t. Okay. And you could write it down anyway using the cumulative distribution function if you want or not. Okay, so if it's not exponential, then it would really depend on what this t value is, because this CDF would depend on what t is, and you wouldn't have that things just cancel out as nicely as in the case of the exponential. Okay, so t is the time right now, that is the number of miles a battery has run till now. Okay. All right, there's a couple of variants in the book for the exponential random variable. And one is called the Laplace distribution. In this case, the random variable is just as likely to be positive or negative, and the Laplace distribution or the Laplace random variable the density is, well, what do we have for a binomial for an exponential random variable? Lambda e to the minus lambda x. And over here, you have lambda e to the minus lambda. Instead of x, you have an absolute value of x because it is symmetric about the y-axis. You get the same density function whether you have positive 3 or negative 3. It's symmetric that way. And of course, now this won't integrate to 1. This will integrate to 2. So you need to put a 1/2. All right. So this is a Laplace distribution, and it is equally likely to be either positive or negative, and it is like taking the exponential random variable and having it on both the positive side and the negative side, but of course you needed to divide it by 2. All right. And you could find what the distribution function, CDF, or the cumulative distribution function for this is, work it out. It's given to you in the book. And then another special case that we could look at is the hazard rate function. Okay. And what you have in the example of a hazard rate function, you're looking at the function lambda t. What is lambda t? It is f of t over 1 minus f of t. Okay? And what you're saying is, suppose the item survived till time t. And we want to know what the probability is that it's going to die very soon. Okay? So what we're asking is, what is the probability that the lifetime is between t and t plus dt, okay, given that it is surviving right now. So right now it's t time t. So given that the lifetime is bigger than t, what's the probability that it just dies in the next instantaneous period of time? And if you take a look at this and work it out, what do you have? You have that this is, just doing the conditioning, once again you have the probability that x is in t to t plus delta t when you intersect it with x bigger than t. If you take a look, the numerator, you'll get probability that x is in t to t plus delta t, or dt, and divided by the probability that x is bigger than t. Okay. All right. And so what do you have? How would you look at this? What's the probability x is in t to t plus dt? We have seen this. We discussed this before. Loosely speaking, you can think of this as the density times dt and divided by what is the probability x bigger than t? That's 1 minus the probability x less than or equal to t. So that's 1 minus f of t. All right. So therefore you have this the hazard rate function. It measures the conditional probability intensity that a t-year-old item will die. All right. And for an exponential random variable, you can check this, what will lambda t be? Okay, you know it's f of t over 1 minus f of t. All right, if you work it out, what will this be? It'll be lambda e to the minus lambda t. And what is capital F of t? It is 1 minus e to the minus lambda t. And so that'll be lambda e to the minus lambda t over e to the minus lambda t cancels, and it is just lambda. So if x is an exponential random variable, lambda of t is just the constant lambda. You could have instances where lambda of t is not just the constant lambda. Maybe it could be that, and this makes sense because over here for an exponential random variable, you're thinking things like, suppose it has already run 10,000 miles. Well, now what's the probability it'll run an additional 5,000? That's the same as if what's the probability it'll run 5,000 miles starting from with a brand new battery. So you see that the likelihood of the battery failing at any time doesn't change, it's the same. But in many practical situations, you do not have that. The likelihood that a battery will die could depend on the age. If it's gone 100,000 miles, then you would expect that, well, it's going to fail any second, something like that. Okay, so anyway, we will look more at this in examples. We're going to do some examples and have just some kind of a video of some problem sessions or examples that we do. Okay, well, that brings us to the end of the exponential random variable. So, and we've finished covering most of chapter 5. Of course, there's some left, but that's the end of 5.5. All right, so I hope that made sense, and you'll be able to do a lot of the problems from chapter 5 at the back now that you've done 5.1 through 5.5. All right, so good luck, guys, and stay safe.